Hey guys, happy Tuesday here. This is maybe my last recording for you guys here before it's the end of the year, and maybe my last recording ever, at least for you guys. So I'm gonna go over 4 limit questions on your tests here, and a little bit about vectors. Um, Not too much though, because it's you could do this for 2 days worth of material, and we just don't have time. All right, so anyhow, vectors are very important for physics, if you're ever taking physics. So if you're not taking physics ever, you really don't need vectors too much, but still a neat thing there, vectors. Um, all right, so first let's go over these ones on your test that a lot of people missed here. Um, okay, so number 7. All right, so number 7, the limit does not exist because they give you this piecewise function, and you are going to 3, okay? Now, you're going to 3. Now, a limit exists if, okay, if you go to 3 from the positive direction and you go to 3 from the negative direction, okay? So you go to 3 from the left and you go from 3 to the right and you get to the same point. Well, if you go from the left, you get to the point around 1, and you go from the right, you get to the point around 3, but in actuality, it's at 7, okay? These must be equal, okay? These limits must be equal for the limit to exist. So that's why this one doesn't exist, all right? If these two limits aren't equal, then there is no limit here, okay? So you can go back to your notes and look at that, but that's a key thing about limits. The left hand limit and the right hand limit must both approach the same number for the limit to exist. All right, so anyhow, in this particular one, number 8, it said identify vertical asymptotes. All right, and what is the limit doing? So if you don't know, okay, look at the graph, but first, all right, you better remember that there is vertical asymptotes because you're dividing by 0 at x equals -9, okay? So x equals -9 is a vertical asymptote because you're dividing by 0. Anytime you divide by 0, it creates a vertical asymptote unless that factor cancels out with the numerator, and then you have a hole, if you remember. That's like way back, like 5 months ago. So, but anyways, if you look at the graph, okay, let me put the graph on here. You can see it. All right. Yep. Get this thing out of the way there. Okay. So, if you look at -9, you could see that it's going down, but it's not getting past -9 here. All right. So there's a vertical asymptote there. It's not connected to this other part of the graph. And it looks like the y value is going to infinity. So remember, the limits tell you what the y value is. So y is approaching -infinity because it's going down, 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 down. All right, let's take a look at this one. Now this one, you might not have any clue what's going on this one. That's why you should look at the graph. Now if you substitute 0 into sine, okay, you could think about what sine of 0 would be, but here you have dividing of 0. Sine of 0 is actually 0, so you have 0 over 0 if you do direct substitution. 0 over 0 is kind of indeterminate here. Sine of 0 is 0. But let's look at the graph and see this is not equal to 0. 0 divided by 0 is not 0, it's not 1, it's not 0.5. Okay, if you went and looked at the graph of this, which you should always do when in doubt here, you could see that as x is approaching 0 from the left side, it looks like it's going to -infinity. But as it's approaching 0 from the right side, it looks like it's going to +infinity. And because there is this disagreement between the left hand and the right hand limit, the limit does not exist. It's pretty much exactly the same reason why the limit doesn't exist in number 7, if you think about that. All right, so hopefully that helps you understand that one. All right, finally, number 10. All right, so this one, okay, you can kind of intuitively figure out this one just by thinking substitution, okay? So I have infinity, okay? If I directly substitute infinity in here, I have infinity times cosine of 1 over infinity. All right, I don't know what cosine of 1 over infinity is, but it really doesn't matter, because what cosine does is it keeps on oscillating up and down, up and down. So you're taking something that's oscillating up and down, and you're multiplying it by infinity, so your answer has to be infinity. All right, now if you look at the graph, you can figure that out too. Now just remember, if you're looking at this graph here, you're looking at for what y is doing as x gets really, really big. And so you might not know just kind of looking at it, but let's go out a little bit more, okay? Like put a value in and see what happens. You see how y has just jumped up there? If we go out a little bit more, y is even higher here. So as x goes to infinity, y also goes to infinity. Y keeps on climbing and climbing and climbing. All right, time for a little bit of vectors. Oh, yeah. Alrighty, here we are. Let's see what I can teach about vectors in 9 minutes here. Alright, so vectors are something that has both direction and magnitude. Magnitude is like the size of it, such as force or velocity, okay? Non-examples are volume and area. Now, velocity, you might think is just another name for speed, but velocity is speed with direction. Okay, so that's why I say this is used in physics a lot. All right, so here, let's look at the next thing there. So magnitude is the strength, so it has a strength and it has direction. All right, the magnitude you could think of is also considered to be the length of the vector. Usually when you are drawing them out here, you're looking at kind of like rays, essentially. You have a point where it starts and a point where it ends, okay? You represent magnitude with absolute value here, and this little thing on the top denotes that it's a vector, not really a ray, but I guess you could think about it as a ray here, a ray that actually ends. So not really related to geometry, but kind of. So, yes, and there is always a direction to vectors. This next slide tells you how you know if two vectors are equivalent. Basically, if they are facing the same direction and have the same length, they are equivalent, all right? They might not be exactly in the same spot, but as long as they're pointed the same way, they are equivalent. So like if I have a vector here, okay, and another vector of the same length right here, those two vectors are equivalent, all right? So we can represent the set of all vectors that have the same length and the same direction as this vector capital V here, okay? So a lot of times the book will represent vectors with capital, not capital letters, bolded V here, and sometimes they'll put a symbol on the top that looks like a ray on top of the bolded V, so you know it's a vector. This is actually more common to have the symbol on the top there, and I should not use blue, but there you go. All right, so yeah, so they have to be facing the same direction and they have to have the same length to be considered equivalent vectors. All right, standard position of a vector is just when you put it at the origin, so put it at 0, 0, okay? So next thing we're going to look at is component form of a vector. Okay, component form of a vector is the form of a vector which is basically 0, 0. Okay, a component where the initial point is 0, 0 and it has some ending point v1, v2, okay? So when you see these little like less than greater than signs around a vector, you know this is a component form of the vector. So this vector is starting at the origin and going to point v1, v2. So quick little sketch. Let's try that again. Okay, so here is this vector, all right, and you don't know which direction it's going. It depends on what v1, v2 is, but you know you're going to point v1, v2, and you're starting at the origin when you see this component form of the vector. All right, so v1 and v2 are called components of vector v, okay? All right, next, if we have some vector, v1, v2, okay, v1, v2 is the position vector if it has these less than, greater than brackets on it. So you have a directional line segment, okay, that isn't exactly centered at the origin. It's going through some other initial point P, another terminal point Q. You can actually figure out the components of the vector by just subtracting the x coordinates, okay, and then subtracting the y coordinates. You can figure out the components of this vector. All right, so that means that you can figure out vector v by doing this. All right. Now let's look at the magnitude of a vector. Remember, magnitude is another name for length. Okay, so vector v is equivalent to this line segment PQ. All right, so you can figure out the length of a vector by doing basically the distance formula here. So if you don't know what the components are, you could just take the square root of the two differences in the x coordinates of the 2 points on the vector, P and Q, and you add it to the differences in the y coordinates squared. Okay, now if you have the component form of the vector, it's a lot easier. You just take the square root of v1 squared plus v2 squared, where v1 and v2 are the components of the vector. So here, let me give you an example of this. So PQ is representing vector v. What is the magnitude of PQ? All right, I went ahead and did it here. You label your points. Okay, x1, y1, x2, y2. It really doesn't matter which one you call 1 and 2, okay, because it's just the distance formula. But anyhow, I try to go in alphabetical order. So, you substitute into the formula. I got the square root of 40. I simplified it. So the magnitude or length of this vector is 2 square root of 10. Okay, and you see I used the symbol, absolute value symbol for magnitude with the vector symbol inside of it. All right, so now that's how you find a vector magnitude. Okay, vector operations now. Let's clear this ink. Boop. All right, vector operations. Vector addition and scalar multiplication. Okay, vector addition is pretty simple. If you have two vectors, u and v, for vector addition, you would just add the x components, so to speak, together. Okay, so you would add u1 plus v1 if you're going to add the two vectors together, and then you would add u2 plus v2. And scalar multiplication, product scalar, remember that? Scalar, most commonly used letter is k, and it just stretches or shrinks the length of a vector, essentially. So ku is k times the vector u, and k just distributes into the vector. All right, so let's go ahead and do some of these operations here. We have two vectors u and v. Let's go ahead and do the operations. And you just kind of follow the order of operations here. So you have 3u, which means you're multiplying vector u by 3. Okay, so 3 times 2 negative 1 will turn into 6, okay, because 3 times 2 is 6. And then you have 3 times negative 1, which is negative 3. All right, so you have 6, negative 3, and you're adding it to vector v, which is at 5, 3. Okay, so we did the scalar multiplication part. Now we have to do the addition of these two vectors. So you just add the two components. Okay, so you add the 6 with the 5, because that's the x component of the vector, and you add the negative 3 with the 3, which is the y component of the vector. So you end up with 11, 0 in the end. All right, we're on the last thing I'm going to show you this year, and that is unit vectors. Unit vectors are vectors that have a length of 1 to them. So what you need to do to get a unit vector, we often use u. Okay, you take vector v, and then you divide it by the magnitude. Okay, remember how you determine the magnitude? That's the square root using the distance formula, all that. So let me show you an example here, and that's it, guys. So here we want to figure out the unit vector of 2, negative 3. All right, so remember this is the simplified version of finding the magnitude. When you have the components, you just square each of the components, you add them together, you take the square root, so I got the square root of 13. So then you just take the original vector v and divide it by the magnitude, okay? So you have 2 over square root of 13 and negative 3 over square root of 13. All right, that's it, guys. Have a great day.